So we have another MATHCOUNTS national sprint problem. So this was the last question in 2024. So we have a figure which is a tetrahedron, right? And then three sides are given 4√3, and other three sides are √21. And we want to find the radius of the largest sphere that can be inscribed in this tetrahedron. So the question is clear, but it's not really clear how to actually get that radius, right? Because you really cannot easily visualize that like sphere. Even if you do, it's not like obvious how to get that, right? So what I'm going to try is finding the volume of this tetrahedron in two different ways. One is just like just finding the base area and multiplying by height, taking 1/3, which is kind of obvious. But the second way is gonna be, just imagine like the center of the sphere is somewhere here. When you connect that center into each side, each face, you actually have only one point of intersection, which is gonna be the point that is gonna be perpendicular, like the face that will be perpendicular to your radius. I hope that is clear. So whenever you take that radius as your height to each face, you can kind of dissect this figure into four different like pyramid and add those volumes together to get the volume of this original one. So what I'm trying to say, let's say the center is like O. So if I take the volume of like OABD, which is going to be just one pyramid, right? And then if you add this to the volume of O like BCD, which is also one of the face cis, and then we got that another like pyramid. So that should be ABD, and then that will be OBCD, and then we will get another face is ACD, so OACD, and then ABC with O, right? So volume of OABC. So when you add those four like pyramid, so you will get the volume of the entire tetrahedron, which we can find as like finding the area of the base, which is I can take as ABC, right? So which will be volume of the, I will say ABCD. Okay, so if I can do this two different ways, that should be good. But we are lucky because, you know, each faces, like lateral face, I would say, if I think as ABC as my base, are actually identical. So which is why we can just find one of these areas and multiply by 3. So it says to be clear. So I'm going to take one of those faces, lateral areas, and I can just do the ABCs as well, because I need to know the area. So that's why I just want to kind of drop the altitude, and the same thing with the other one. So imagine this is like A, B, and D. So this is height, and then this is like ABC. ABC is equilateral triangle, so that should be 4√3. So if you want to find the area of the equilateral triangle, there is a nice formula, right? We have S squared times √3 over 4. So if you square this side, which is going to be 16 times 3 is 64, like 46. 46 divided by 4 is 12. So 12√3 for the area of this triangle, or you can just use it 3690, which is this is going to be 2√3. This is 4√3. This has to be √3 times of this, which is 6. So you can just use this as well. If you do that, you get the same area. And this guy has √21 for this isosceles side. And the base is 4√3, which is 2√3 and 2√3. And if you use the Pythagorean, that's 12. This is 21. So that should be 9, so which is just 3 units. And now if you want to find the area of this region, so that will give us 3 times the base is 4√3 divided by 2 is 2√3, which is 6√3. So now we know the the area of ABD or DCB or DAC are equal, which is 6/3. And the volume of a pyramid was the one third times the height. Height is in all cases radius, so I'm gonna just write as R. And instead of writing 1/3 times R in every one of these, I'll just put as a common factor. And the base area for the lateral face is just 6/3. So we have 3 of those, 3 times 6/3. And the last one, OABC, which is the base one, was 12/3, right? So that should be 12/3. And the volume of this figure, and without really doing this dissection, so we can actually get the height of the prism, the pyramid, when you take the ABC as your base. So if I take the centroid of the base, that should be my center, right? So, and if I connect this to D, that will make my altitude. So let me do that. So we know this is BC is 4/3, so which means 2/3 and 2/3. Since this is a equilateral triangle, so you can just multiply this by √3. This is gonna be like 6 as this one. Since we have this as my centroid, so that should have 1:2 ratio. G to this distance is 2, when A to G is like 4, so 4:2. And if I use the Pythagorean in this triangle for √21 and H, so H has to be just √5. So now we are almost done with the area. So volume. So volume of this will be 1/3 times base area. Base is just the equilateral triangle. We know the area is 12/3. And the height is √5. And since we know the 1/3 and 1/3 will cancel each other nicely, that will be 18 plus 12, which is 30/3. So the R times 30/3 is gonna be 12/3 times √5. So these guys also cancel, divide by 30. So we'll get R as 12/5 over 30 divided by 6. So that should be 2/5 over 5. So I think this is my answer. And the question wasn't really too challenging, to be honest, especially for the last question, but it wasn't really clear how to start. Maybe for some people, I think this is a good one to try. And if you are kind of looking for another challenge based on this problem, I would say try to find the center of that circle, not circle, like sphere, as I will say coordinate, like put these like on a coordinate plane and like kind of like, I don't know, make some sort of XYZs in 3D. And based on those, can you find a general, I will say, formula for either finding the radius of the sphere or general formula for finding the center of the sphere if you can. That would be a good one to try. And also, if you have somehow the vector like background, can you try this problem in a different way by using vectors? So that might be the one to explore as well. So anyway, I'll see you in the next video.